put up a what courses, for example, or these slides. So, the analogy I like to use is stacking dinner plates when you have one plate on top of another, or you remove a plate from a stack of plates. So the concept of adding to a stack is called a push. And when you remove something from a stack, the terminology is a pop. So this is just an image that shows you we have 5 plates stacked on top of each other. So the very top is always that last one that got pushed onto the stack. I kind of like the idea of heads. You got little heads. Yeah. Can you show it then? Push one down every time. So when we add those stacks, it's also referred to as a push down stack. So that's what means when you're just adding a new element or an object to the stack, and you have to push it on there. And so I love to do it. How to properly load a pen candy dispenser, because this is such a difficult concept. Figure we start out with a little bit of fear. This is really hard, huh? Wow. It is. You know, everything in life could be made into a YouTube video. Well, he's going to shove that whole thing in there. The pen containers I have, we have that with really just load them like that. We have to push one on and hold them. So now you can put a whole stack in there, and now you can pop one. How cool is that? But you do other pictures? Because you got your money worth? Sorry, okay. Well, you're not going anymore. Okay, so when you remove one from the stack, you pop it off. So that's how you get the candy out of your pen container. So pushing and popping, they're inverse operations. If you push an object onto a stack and then immediately pop it off, your stacking itself hasn't really changed. Right? So why do we even care? Well, we care because push down automation is a very key role in a lot of things we do from a programming perspective. Parsing the data, translation of expression, calculation of source code. A lot of the stuff that happens in the background that you don't even see is using stacks to make that happen. So for us, the reason why we care is we want to understand recursion, and it'll make it easier for us to understand recursion when we understand stacks. So they use stacks are used as a memory structure. So just like a linked list, it takes up memory. And it plays a key role in how your executable statements are processed. So we were talking about, last week, Wednesday, we started talking about recursion, and I drew out that picture of how the multiple function calls got stacked on top of each other. And once it got to its base case so that it could exit out of the recursion, it then started popping all of those function calls off and executing them one at a time. And so we use this as stack activation metrics, and it helps keep track of the sequence of function calls. And so this is what really helps us understand recursion. And I highlighted this last week that the implementation of a stack is last in, first out, or LIFO. So you can't get something from the middle of a stack. You have to always operate with whatever on top. And that guy that's on top is the last bit, because it's going to be inverted out. So let's look at source code that highlights all of this. So on what courses, there's stacks.cs line with our linked lists and our recursion and everything, we're going to use a node. And so we have this node, and we have our one part that's info, and our other part that is a pointer to the next. And then we have 3 global variables referencing, declaring. We have 3 global declarations here. One is top, one is top 1, and one is top 2. My function prototypes. So I have these functions. One is top element, one is push, one is top. And you'll see that when you're implementing stack, we did use the functions called push and top. That's what they are. So I changed terminology. It just makes sense. And then we have this other function, empty, display, store, stack, count, and create. Then we have a global variable called count, and it's going to be initialized for the value of 0. So in my main, I have 3 variables here of type int, and then I have a memory system. So the memory system is going to let the user control what happens. So we have our options. You'll see that each one of the many options correlates directly to one of the functions, with the exception of the create. So the create here, its purpose is to actually create a stack. So, and then we have a while. So we're just going to continue to loop until we're using that something like that. Something I did, this makes me absolutely crazy. I really don't like this one thing. But that's just how C implements it. So my workaround actually was, you'll see this in my code. I really like having my little true. So I did a pound and find, and I created a variable, a constant called true, and I set it equal to 1, so that I don't have to use that 1. So, but that's how, this is how it's implemented. Okay, so the user in the main, we're going to go through this. The user's going to have a choice. We're going to enter their value. It's going to be stored into the address of variable ch. And we're going to do a switch on that ch variable to find out what the user wants to do. If they want to do push, here's the function. We're going to ask them for a number to push onto stack. And we're going to pass that function as an argument. If you want to remove one from the top, we're going to do a pop. And then here, we specifically are going to get the top element. Here we're going to empty the entire stack. This is our edit. We're going to display our stack, and then we're also going to do a count. Or completely distort it. Yeah. Okay? So let's look at the create. The create, all it's doing is just initializing. So I have one function. Alright, so it just initializes our global top. So top is going to be the same thing as what we consider head. And we just initialize the null to make sure that when we actually create that stack that we're putting the data on the linked list. So now we have our count. And the count is just going to return the global variable count. So here's our push. So we're going to push data onto the stack. So what's going to happen is we're going to get that value in that we want to put on the stack. We're first going to make sure that our stack is not null. And if it is null, we're going to go ahead and do the malloc, create a new node. Then we're going to set the linked portion of our node to null because we have nothing on our stack, so we want to make sure that we just set it to null. And then we're going to set our data. If we're not null, we're going to use temp to allocate our memory. We're going to set our link equal to top because we're pushing down. Okay, so it's the same thing that we did when we were doing the linked list example. and then we're explicitly adding to the beginning. So it's the exact same concept. So if you're comfortable with the linked list example here, so it's the exact same thing that we did when we're adding a node to a linked list at the beginning of the linked list, where we are pushing onto the stack so that our next on our node is equal to head. Because again, if you go back to look at this concept right here, so we want this is our first one, and then when we put a second one on there, we're going to say that my next guy is here. So it's always going to be at the bottom. So then we're going to reset our top so that it's equal to 10. If we want to point to the last guy, we want this to be top. See that? We always want the one that's on the top to be called top. So we first have to create the linkage to push this guy in front of the current node on the stack, and then reset our stack. We have a display. What display is going to do, we're going to use this top one global variable and initialize it to the actual head top, and then we're going to check to see if it's null. If it's null, there's nothing on our stack, so there's nothing to display. So we're just going to return if that's the case. Otherwise, we're going to loop through our stack, and we're going to output the data that's on our stack, starting from the top, going to the end. So while we are not null, because this guy right here, his pointer is going to be null, because he's the last guy on the stack. And that's how we know that we've done looping through our stack. So it's just like the linked list. It's just a different terminology and how you actually deal with it. Here's our top. We're going to use our top one so that we can, as our helper, so we can move through it, and then we set it equal to the head. And again, if it's null, obviously there's nothing to remove, so we're just going to return back and say there's nothing on our stack. Otherwise, we're going to come down here, and we are going to first, if you remember from the linked list, when we go to delete, if you remember on the linked list, when we went to go delete, before we deleted that node, we had to make sure we reset our actual pointer. Remember that? You have to reset that pointer first. And if you delete it, then you're going to lose the reference to it, just like in the linked list. So we're doing the same thing here. We're first going to reset our pointer so that we have reference to the second node from the stack. And then we're going to go ahead and delete that guy, and then we're going to reset our head back to the second dude. So what happened here was we have the value 5, and we want to pop that off. Before we can pop that off, we have to move top down to here. Does that make sense? Because if you don't move it, you're going to lose the reference to it. So first, we're going to move his reference to here, to item 4, and then we can go ahead and pop that guy off. And then here, this one is just going to function is going to return our top element. And then empty is checking to see if our stack is empty or not. And then destroy is going to go through the entire linked list and free the memory for each node that's on it. And then it's going to set top equal to null. And then we'll have an empty stack again. So it's very similar to how linked lists work. So here's our code. I'm going to push a value on there. And then I do my display. So it outputs the value of 12 that I had on there, so I'm going to push another value. See my display. Let's push a few more values. Okay, so when I display this, you see that every value I put on there, when it displays the data, the very first value I put on my stack is 12. And that's the last thing that gets displayed, because it got pushed to the bottom. And then I set a value of 45. 45 got pushed on top of 12. And then I have my value of 23. I pushed 23 on there, and then 67, 89, 85. So 5 is now our top element. And I can prove that to you in item 3. And you see 5 is our top element. So that's the value that's right here. If I ask if my stack is empty, it says it's not, because I have 7 elements on it. I can display my stack. I can do a stack count. Item 7, it just tells me that I have 7 items on my stack. You can prove that by doing a display and physically counting them. You can see all 7 of them. And then now let's deal with popping. So we want to pop a value off. So let's see what happens if we try to pop 23. Because I can't. I cannot take the value of 23. Because it's in the middle of my stack. It's not on the top. And so it's not going to let me pop off a value that is not in the correct order or is not on the top. So this is where linked lists and stacks differ, where you can delete whatever you want from a linked list. You just have to find in the linked list where that value is at, and you can go ahead and delete it. Stacks will not let you do that. This is a stack. It's similar to a linked list, but it's a stack. And I think the difference between linked list and stack is that how they are created, and that you have to force that you cannot take anything off the stack. Whereas in a linked list, you can do anything you want, and you don't take it off. So I'm going to try this again, and we're like, what? All right, so it won't let me look at 23, so let me try 5. It says, oh, okay. And so it, oh, did I? Yeah. Okay, so. Okay, so here's my values that match what's in the stack here, 1 through 5. Now if I try to pop off the 1, or if I just run the 1. Okay, so now I want to pop that top element off. So I enter the value, and it just automatically goes in and does it for me. So I don't have to pass a value on the top, because the only thing it's going to do is let me pop off that very first node that's on the top of the stack. So this implementation is very similar to linked list. Yes? To force this format. If there are situations where you want to use this stack, and because you don't want to be able to randomly delete data from the middle. Especially if your data set is sometimes sequence in order. Like if we're outside of something like that, we want to make sure that So with liquid, you have the freedom to use them anywhere where it's that. The only way is to take them off from the top. Anybody have any questions about it? No? You stop talking? This went a lot faster than I thought it was going to. Either you guys are just like ignoring it, or you kind of go on, I just want to go away. So there's no questions or concerns. Those are cubes. Cube. A cube is first in, first out. Okay. So when you're doing a cube, it actually is in order. So if we, the way a cube would work is kind of like you're queuing up in a line. And so the first person is first person in the line, and the first in, you're the first out. Give it at item one. Item one would be from a cube perspective. The other implementation of doing that. Yes, sir.
If you were to pop off 5, how would you send force across?
Okay, so we have our helper guide here called top 1, and we set it equal to the head, and then if it's not null, if it's null, we're going to return nothing. So here, the first thing I do is set top 1 equal to the address of the next item. That's what this one right here is doing for us. So from a visual perspective, if you correlate it to the side, okay, so this right here is saying move my pointer from here and make it look here before we get rid of it. Then we can go ahead and get rid of that guy. We're going to free it, free the memory, and then we reset our head or our top to our helper guy so that now our top is looking at this as well. Does that make sense? Yes. Okay, so from the data itself, the liquid, it has the data organic one, and it has them when you use those to know okay? With the liquid, you have the option of removing a lower somewhere in the middle of the data. With that, cannot be. It has to be the one. It has to be one. You're not allowed to take the node off in the middle. This is simply an example of that. Because what happens is we read that first one and it gets repeated. Here's the second one, here's That's how it differs from a linked list. So if in a linked list, okay, so here on a linked list, if I do an insert, right, I insert the value of 1. And then I do display, and I have the value of 1. I insert 2, insert 3, maybe. Getting too quick to my memory system here. Insert 1, insert 2, insert 3. Crashing is what it's doing. That's awesome. All right. Woo! What is this? Good? Yeah. What is my coding error? And infinite loop. Killer. That is so much fun. All right. Let me find a linked list that actually works. Hold on a second. Oh, for F's sake. There are gremlins in my computer. It's a Monday, isn't it? Okay. Oh. This is why I absolutely hate coding real time. Yeah, it's awful. Okay. But what happens is when I'm working with you guys, I make modifications to my code when I'm trying to help you do your code, and I never go back and fix mine, and then it's also stuff. I'm like, what is going on here? There we go. Holy mother of God. Okay. So, the linked list. So I just added all the data on it. Now you did it in sequential order from beginning to file. I have the option of deleting an item in the middle. And then, so now that guy in the middle is gone. Stacks do not allow you to do that. That is not an option in stacks. You have to delete from that option. So if we were to use the same exact one, and we were using it as a stack, you would have had to have deleted George Washington. You would be the only one who could delete. And you wouldn't even use this call function problem. You would take that out. You would even ask them for info which one you want to delete, because it's going to delete. So from that perspective, that's how the limit is set up. And so you force that implementation when you know that you don't want the user to be able to do it. So that's from a construct, from a load construct. is very similar to element nodes. They both use the nodes, they will have pointers. Okay? But what makes them is they're different in the stack of what is easier than others. Right. You tell them no. And you're not.
I think a good thing to point out is that you can do it using arrays. The stacks.
Oh.
Implement stacks with arrays. So that way they don't get locked in as soon as you always need to use them.
So what Jonathan is saying, from our perspective, I use nodes because that's where we are in our discussion. We're going to make this and stuff like that. But if we look at it from an array perspective, it works the same way. So you don't have to have the pointers. So if you want to look at it from that perspective, if we have just a regular array, so we're just looking at data. If we implemented a stack with an array, the user would only be able to delete the number one, or pop off the number one. So if you don't even want to think about the node perspective, this is another way to think about this. So for an array, implemented as a stack, what this would look like so when I put my data on my stack as an array, my value 10 is on the bottom. Okay, just think of that visually.
Would this then be on the top of the last one?
Because it doesn't do it. Right. I push the data on there in this order. 10, 9, 8, 7, 6. This is after the data. This is on the top of my array. So this is the one that would get popped off. Then you think of the data, and I said, okay, I'm putting this value on my stack. I'm putting the value 10 on my stack. This one, put the value of 1 on this first. 2, 3, 4, 5. So if you think of the data vertically, you look at the data here vertically, this is my top. Okay? That's the number one. Did I do that right down there, or screw that up?
Yes.
Okay. Yes. That was one or another there.
I think the main thing that I would point out though is when you implement it, when you have stacks, you're going to have functions that check if it's full and if it's empty. When you have linked lists, you don't care if it's full because theoretically it'll never get full. With the arrays, you want to use that is full function just to make sure that you implement that.
That's a valid point. So what Jonathan's saying is when we do a stack implementation using nodes, there is no size limit, but you know with arrays there are. Okay? So what he's saying is in this case we have to check if the data array is full. because it's a raise, they have to find that stop, right? So when we're dealing with a raise here, if we did stacking and teaching and raise, stacking, we have to make sure that it's full. And so that would give us another function that we would have to implement from a stack. Does that make sense? Because if you go outside the bounds of your array, you're going to have errors, all kinds of problems. It'll probably let you put it on there, but you're causing problems on the back end for memory. Any other questions? No? Sure. You have 12 more minutes of my time, so if you need help with something like your homework or whatever, I'm here.